Artificial intelligence is often portrayed as an unstoppable force, an ever-evolving intelligence that surpasses human abilities, automates tasks, and unlocks new possibilities. But beneath the breakthroughs and marvels, machine and deep learning systems remain deeply flawed. They are not omnipotent, not infallible, and certainly not free of limitations. These systems struggle with bias, interpretability, efficiency, and real-world unpredictability. They require vast amounts of data, expensive computational power, and careful human oversight. They can misinterpret, deceive, or amplify existing inequalities. And, at their core, they remain narrow intelligences, powerful within their domain but fundamentally incapable of true reasoning or consciousness. Understanding these challenges isn't about diminishing AI's achievements. It's about recognizing where AI still fails and what must be done to push its boundaries further. The illusion of intelligence. AI can write poetry, compose symphonies, and beat humans at chess. But does that mean it understands? The answer is no. Machine and deep learning systems do not possess understanding in the way humans do. They recognize patterns, predict probabilities, and generate outputs that seem meaningful, but they do not comprehend meaning itself. When an AI generates a poem, it does so by statistically predicting the next most probable word based on existing literature. It does not feel the weight of the words, nor does it grasp metaphor or emotion in a conscious way. This limitation is especially apparent in areas requiring common-sense reasoning. AI can identify objects in an image with astonishing accuracy but might fail a simple test like understanding why a stack of books will fall if the bottom one is removed. It can generate convincing-sounding text but may contradict itself within a few sentences. Deep learning models simulate intelligence, but they do not think. They do not ask why, they only respond to what. The data problem. Quantity over quality. Machine and deep learning models thrive on data. The more data they have, the better they perform, or so it seems. In reality, data quantity is not the same as data quality, and this dependency on massive datasets introduces significant challenges. First, there is bias. AI models learn from the data they are given, and if that data is flawed, the AI inherits those flaws. If an AI is trained on historically biased hiring data, it may favor candidates from privileged demographics while rejecting others. If a facial recognition system is trained predominantly on lighter-skinned faces, it may misidentify people of darker skin tones, something that has already happened in real-world deployments. Second, there is data scarcity in critical fields. While internet-scale language models benefit from billions of text examples, medical AI systems often struggle due to limited access to high-quality, diverse datasets. Medical records, legal documents, and other specialized domains lack the abundance of freely available data that AI thrives on, making training more difficult and models less generalizable. And then there is data noise. AI models struggle to distinguish between meaningful patterns and random noise in datasets. They can be tricked or manipulated into making incorrect predictions, a vulnerability exploited in adversarial attacks, where seemingly insignificant changes to an image or input data cause the AI to completely misinterpret it. Interpretability. The black box dilemma. Deep learning models are often described as black boxes. They make decisions, but understanding how they reach those decisions is incredibly difficult. Unlike traditional algorithms which follow clear, rule-based logic, deep learning systems operate through millions of interconnected neurons, forming relationships that even their creators cannot fully explain. This lack of transparency creates problems in fields where trust and accountability are paramount. A medical AI diagnosing cancer must be able to justify why it flagged a certain scan as malignant. A financial AI approving or denying loans should be able to explain its reasoning. But deep learning models struggle with this level of interpretability. Efforts are being made to address this issue through explainable AI, XAI, techniques designed to make AI's decision-making process more transparent. These include attention maps, which highlight which parts of an image or text influenced an AI's decision, and rule extraction methods that attempt to translate complex neural reasoning into human understandable logic. But full transparency remains elusive. Until AI can reliably explain itself, there will always be hesitancy in deploying it for high-stakes decision-making. Computational hunger. The unsustainable cost of deep learning. Training deep learning models requires immense computational power. The largest models today consume hundreds of thousands of dollars in electricity alone during training. Some estimates suggest that training a single cutting-edge AI model can generate as much carbon emissions as 5 cars over their entire lifetimes. This raises concerns about AI's environmental impact. As models grow larger and more complex, they demand more energy, more hardware, and more infrastructure. The industry is already experiencing hardware shortages, with GPUs and TPUs becoming increasingly expensive and difficult to obtain. There is also an economic divide in AI research. Training deep learning models at scale requires enormous financial resources, meaning that only a handful of companies and institutions, mainly tech giants, have the ability to push the field forward. This concentration of AI development in the hands of a few raises concerns about accessibility, ethical oversight, and the monopolization of AI's future. Efforts to develop more efficient AI architectures are underway, including pruning techniques, quantization, and neuromorphic computing, approaches aimed at reducing AI's power consumption. But as of now, the trade-off remains. The more advanced AI becomes, the more costly it is to build. The real-world unpredictability of AI. Machine learning models are trained in controlled environments. They are fine-tuned on carefully curated datasets, optimized for structured inputs, and tested under ideal conditions. But the real world is chaotic, ever-changing, and full of unexpected variables that AI struggles to handle. Self-driving cars, for example, perform well in structured simulations but have repeatedly failed in unpredictable real-world situations. A person walking in an unusual manner, a plastic bag blowing across the street, an accident that blocks an expected route. These can all confuse an AI system that has never seen them before. Similarly, AI-powered customer service chatbots function well until they encounter sarcasm, humor, or cultural nuance. Speech recognition systems stumble when dealing with accents, dialects, or noisy environments. AI models that generate content can produce factually incorrect or misleading information while maintaining a confident, authoritative tone. AI works well in structured, predictable spaces, but the real world is neither structured nor predictable. The path forward. Machine and deep learning systems are flawed, limited, and incomplete, but that does not mean their progress stops here. Understanding these limitations is the first step toward solving them. Research in hybrid AI models, which combine deep learning with symbolic reasoning, aims to improve interpretability and logical reasoning. Advances in energy-efficient AI architectures seek to reduce the environmental and economic burden of AI training. Ethical frameworks and bias correction techniques are being developed to mitigate unfairness in AI decisions. Improved self-supervised learning is reducing dependency on massive labeled datasets, making AI more accessible and adaptable. The road ahead is filled with challenges, but that is precisely what makes AI development worth pursuing. True intelligence, whether artificial or human, emerges not from perfection, but from the ability to recognize and overcome limitations. For all its flaws, AI is still evolving. The question is not whether it will surpass its current constraints, but how, and when, it will redefine what we thought was possible.